Okay, thanks, Steve. So I'd like to make 3 remarks on eternal inflation when looked at from a quantum cosmology viewpoint. And really, this is just to set the scene for hopefully further discussions during the program, right, on this subject. So first, I'll make a statement about how we detect or how we see eternal inflation in the context of quantum cosmology. My second remark concerns how, in the context of quantum cosmology, we derive predictions for local observations in eternal inflation. And finally, I make a remark on eternal inflation from a holographic viewpoint, and I'll end, time permitting, with a conjecture. So most of these, what I'm going to say, is based on discussions and papers with Hartman and Hawking, and some ongoing work with students Oliver Janssen and Gabriele Conti. Okay, so what is eternal inflation? Well, you can think of eternal inflation, broadly speaking, as Steve said, the deep IR in cosmology. Either the deep IR beyond the IR cutoff that we impose in perturbation theory and that we saw in Martin's talk and in Sarah's talk last week. Or you can think of eternal inflation as the far past, the regime of the universe before the 60 e-folds that we observe on the microwave scale. So, what does a quantum cosmological perspective add to the game? Well, in quantum cosmology we begin with a wave function of the universe. So why do I want to do that? Well, I felt kind of obliged because the psi is in the middle of the wiki page every day. But other than that, it buys you 2 things. If you start from a quantum state, all the rest is implied, emerges as a prediction rather than as an input. Firstly, the regime of the universe which we usually are interested in, classical cosmological evolution. That emerges from a quantum state of the universe under the conditions or in the regime of superspace where the typical WKB approximation holds and the phase varies much more rapidly than the amplitude.
By the way, the question is which psi is in the middle of the wiki page?
That's true. That's true. Although that's not very obvious from your logo, but
Okay.
yeah. Yes, but for now I'm just setting the scene. So if those conditions hold, then the wave function will predict that this particular configuration evolves like a classical cosmology. Of course, the wave function is a function of various configurations, so it will predict naturally an ensemble of classical universes. And each of these universes comes with a certain amplitude because along that classical trajectory that emerges as an integral curve of the phase, the amplitude A is conserved. That's a consequence of the Wheeler-DeWitt equation.
Excuse me, what are these gradients with respect to what?
These are gradients in superspace. So with respect to the configuration in superspace. So the natural observable, so to speak, or the natural diffeomorphism invariant quantity that emerges from a wave function are 4 or 10-dimensional, 4-dimensional histories for which the wave function assigns a measure or probability distribution. We interpret these guys as probabilities for histories precisely because they're conserved, the amplitude is conserved along those classical trajectories. So we have some measure, that's what we get out of it. We have a framework to detect to what extent the approximation of classical cosmological evolution holds, and secondly, the theory comes equipped with a natural measure determined by the quantum state. So now, in order to proceed and be more specific, one has to specify a state, and I'll work with the Hartle-Hawking state, because that's the one I understand, and that's the one which is well motivated also by fundamentals. Hartle and Hawking's idea was to provide a weighting, so now I'm taking the scale factor out, I'm considering a mini superspace model with gravity and a scalar field, some potential, which at least has here and there patches where the conditions for inflation hold, and so forth. And so Hartle and Hawking's idea was to weight such a configuration with the action of a compact regular saddle point matching onto that configuration at late times, weighted by the Euclidean action of that configuration.
Can I ask a question? There's a long literature on interpreting, on the impossibility of interpreting model square of psi as probability, this conflicting with standard quantum mechanics. Do you have anything to say about that?
Well, as I mentioned, we're going to interpret this as probabilities, relative probabilities, for different four-dimensional histories.
I mean, there's a long literature on that saying that this is wrong. Do you have any? No discussion.
I'm not going to discuss.
Okay.
Well.
Is there a
may I
you're
make
saying
it
it's
that?
wrong in the semi-classical limit?
So you say it works in the semi-classical
I think
limit?
it works in the semi-classical limit. Which
At this level,
which
this
is what
is-
he's studying.
Huh?
Which is, he's studying just the semi-classical limit, and I think it works there.
It works. Okay.
Yeah. There's the key question, of course, how to extend this beyond WKV. I'll come to that. This is
Okay.
my third remark, of course.
Okay.
Yeah.
Thanks.
So, but at the WKV level, we proceed like this. Okay, so there's a regularity condition all the way at the bottom here. And that's a semi-classical implementation of what one discussed last week. If you have the potential in the Wheeler-DeWitt equation, then essentially Hartle and Hawking's idea picks out the wave function that decays when a goes to 0. And the semi-classical implementation of that idea is very much to impose a regularity condition on the geometry at the south pole of the saddle point. And so what is the... So we have a concrete geometry, a saddle point geometry, that provides us with an amplitude of the different configurations. But this regularity condition picks out a very special, or an a priori very special set of histories, because it implies that these saddle points have the following structure: that up here, when the scale factor is large, you have essentially classical cosmological behavior. That's fine. All the saddle point action, the Euclidean action, goes into the face of the wave function. That has everything to do with the fact that the Wheeler-DeWitt potential is negative. But the key point that the regularity condition implies is that you have an early period of inflation down here, classical slow roll inflation. And that comes about because it's only when the gradients are kept under control at early times that you succeed in rounding off these guys, these geometries, regularly. Without any inflation, gradients both in time and in space essentially diverge.
So just again, when you say slow roll, do you mean h dot over h squared or b prime being small?
Yes, slow roll conditions at the level of the potential, so v prime small.
You mean you allowed for more general possibilities and you are led to slow roll inflation, or
That's right. That's right.
are you saying Hartle
Yes.
Hawking is not consistent with, I'm just curious because if you could make such strong predictions, it would be interesting. Are you saying it's not consistent with, say, P of X models, so to speak,
Which
The
model?
DBI inflation.
for example?
Yeah, DBI, that's an interesting question. I looked at it briefly. I couldn't find any saddle points. But I wouldn't make, that's an interesting question.
I just don't
I'm
see the
not-
connection
I'm not
between
sure.
that and the regularity, but if you're finding
Yeah,
one,
but let me draw a picture. So imagine you have a potential, kind of a landscapey potential. Then what this regularity condition picks up, a priori I can start with any value of phi as a sample. So the regularity allows for an arbitrary value of phi.
But we need to, if we're going to pursue this, which we don't have to, we need to talk about the kinetic terms as well.
Yeah, so I don't know the answer to the DBI
okay.
question. The level at which I was making the statement here was that a priori I have a saddle point for all initial values of phi. However, I will never get to a classical real cosmology if my initial value is not in those patches where the slow roll conditions of the potential hold.
Okay, but I think you assumed canonical kinetic terms. So
Sure. Yeah.
That's fine.
Yeah.
Okay.
But it's a first kind of selection imposed by the state, which selects the inflating patches, or the patches which allow for inflation in a kind of landscape context. Okay, so that is a typical structure of the saddle point. Beyond, further back, the geometry obviously becomes complex in order to round it off smoothly. So at the end of the day, this weighting gives you something of the form of an amplitude times a large phase factor.
And does something change if there's some regions in this potential that are negative? Say there's a negative, there's a minimum at negative values of V?
No, nothing. No, the future history may change, of course. You can develop singularities in the future. That's certainly in the game. Yes.
But it wouldn't really matter for this, because you might think the Euclidean action, would include some configurations. It might care about whether you have regions with negative V.
Well, so you won't easily find saddle points which evolve into a classical cosmology if you start with phi at the saddle pole here. But if you start, say, imagine this is slow roll. If you start here and you roll down, that's perfectly fine. You will be inflated. You will have
Okay, but
a regular
cosmology.
geometry.
I just want to know if something happens to psi when you have a thing like that.
Oh no! This is all. This last business. That's all in the face. Big crunches and all that.
Here you have this e to the minus s Euclidean. And I think s Euclidean cares a lot whether you have v negative or not.
Well, it cares in the sense that it will exclude those regions because there are no regular saddle points. So the probability to start here is very low, but you can certainly end up there.
What about the saddle point that's just Euclidean ADS, where I just sit right down at the bottom forever? Right, so phi doesn't depend on time at all. I sit at the bottom.
Yes.
There's
So
Euclidean ADS.
at all these points, you will have these isolated saddle points at all extremes.
Okay. And do those have low probability according to your measure or something like that because the volume is infinite? If it's ADS. I'm just...
Either very low or very high.
They're not classical. I mean, the action would be real. If the real Euclidean saddle points, you never get into any sort of...
Yeah, here that would just be Euclidean.
You know, Lorentz, no. Wouldn't be
So they
semi-classical.
would be infinitely suppressed because of this.
Okay, so they're infinitely suppressed.
Maybe
At the end of the day, we.
No, I think it's suppressed for the Hartle Hawking.
But at the end of the day, I mean, I come to the notion of probabilities and the use of a wave function whenever I have these classicality conditions, right? Or otherwise, I mean, that's going to be part of my point. Otherwise, the interpretation of a wave function is very...
Oh, I see. So
very far
in
removed
the
from-
case I'm talking about, you'll never have
That's
a
right.
phase.
That's right. That's right. Yes, obviously I have Euclidean ADS points. They're just like these hyperbolic guys. Yeah.
By the way, there's another point, and this might be more appropriate for later discussion, but let me just bring it up briefly. So, the Hartle-Hawking wave function is something that follows from a geometric criterion, but right on the geometry. But I think at least many of us expect that in this regime, sort of very early, very small scales, etc., geometry is breaking down. That's maybe not the correct notion. So why should we be determining, and this is really partly a question for both of you, why should we expect that the correct wave function is determined by such a geometric criterion when that's not the right way to describe the physics?
Yeah.
Possibly.
Yes. No. Well, yeah. Very good. So I view this as, so the curvature is everywhere low here, right? In these saddle points.
True.
So, but I view the original sort of description of the Hartle-Hawking wave function as a kind of low-energy effective model of a state. And it would be extremely interesting to derive it from a more microphysical picture. I think this is where part of our goal with the CFT is oriented to. And the best bet is the Euclidean ADS connection, I think, that Juan pointed out.
But I mean, the thing about it is, if it is a smooth geometry, it actually is it's not dependent on the UV completion.
That's the idea.
Because
Sure.
of the way things turn out, it doesn't depend on that either, right?
Yeah, sure, but you would kind of...
You still need a justification for it.
Yeah, like I mean, why not a different...
It's either a feature or a bug.
Right.
Is this low curvature? How low are you? What determines
the curvature? Well, or no, just not even that. Just
the curvature of this approximate four-sphere region is set by the value of the potential. So there's a characteristic scale, which is 1 over the square root of the potential evaluated at a field at the south pole of the center. That's the local Hubble scale during that very early phase of inflation.
It emerges into real-time inflation from a Euclidean sphere, sort of.
Sure. Yes.
So can I ask? I mean, what would happen if you would just do, let's say, some kind of one-loop calculation around that start point? I mean, would that not be some kind of a test that shows how stable that is? And has anybody done that?
Yeah. People like Kamenchik and
Barvinsky.
Have done those calculations. Yeah, sure.
A long time ago.
Yeah.
Sorry, can I return to Carlo's question just for a minute? Because I realize that I said something incorrect or I've linked to the wrong point. Do you really mean that you want to interpret A squared directly as a probability, or do you mean that you're going to map out the semi-classical flows through configuration space, slice across them, and use something more like a Klein-Gordon product on a slice, which would sort of reweight that by a factor of, if you like, momentum along your flow?
We interpret those directly as probabilities for those classical histories, arguing they're conserved because the Wheeler-DeWitt equation has conserved current, right? that assures that these guys
That's not the conserved current. The Wheeler-DeWitt equation is Klein-Gordon-like. The conserved current is like a Klein-Gordon current, which differs from what you wrote there by a factor of roughly momentum in the volume of the universe direction.
So these are relative probabilities, as we call them, meaning we don't have control over the normalization.
But if the normalization
we have a framework, right, which I worked out a very long time ago, right, where you embed this in decoherent histories, where the histories are geometries, the wave functions weight them, and you actually do get out the current correctly in the semi-classical limit.
Okay, I mean that extra factor of momentum certainly can weight one history relative to another, but you say that this will go into some machinery that produces that.
We're looking only at the exponentials, I think.
Yeah, I think what you're doing is prefactor stuff.
But you wrote down the prefactor. You said you're going to
Okay, but the prefactor has an exponential part, which we're mainly interested in.
Fine, okay. at that level, it's correct.
Yeah.
I think that, I mean,
Well, that's
the
right.
semi-classical limit.
But also these loop corrections will feed into those.
Yeah.
So I'm really sorry to belabor this, but I didn't understand the answer to Steve's question. I mean, if you just work in Lorentzian signature the whole time, and you take the state you're talking about, which I agree at late times doesn't directly involve the UV completion, what are you saying about it at earlier times?
If you're just working Lorentzian signature all the time, these are you bump into the big bang
I know,
singularity.
that's the problem.
Well, you have some tunneling perhaps that you have, you have
That's
to
the question.
tunnel.
But tunneling would not be Lorentzian.
Tunneling
Forget about the tunneling, just evolve it that.
Oh yeah, sure.
What are you saying?
No, that's why it's a little subtle, the answer. This is in many ways a statement about how that initial singularity is resolved. And it's formulated in approximate low energy geometric terms, and that's why we need a derivation of that state, I think, from fundamental theory.
All right, so we have some examples.
You could hope then that it sort of provides an approximately accurate calculational framework because the curvature are everywhere low, but somehow one would like to have this emerge from.
I agree. I mean, that's all fine. It's similar to what we say in normal inflation, but we don't claim that that explains everything. So, explaining the whole past would seem to still require understanding the UV completion, I would say, if I'm...
It would.
I would think.
Two ways to view this. Given this state, this is complete.
No, because you don't know what to do just in.
No.
Evolving the state back in time, you don't know what to do.
No. This is a statement about what we do and how classical cosmology emerges.
I mean, I think it's a recipe for some particular set of relatively low entropy states that the universe starts in. And then you evolve those forward.
Starts meaning
no.
There's a beginning to time?
No. There's no beginning of time here. That's the key point we propose.
If there's no beginning of time, what do you get if you evolve it back in Lorentzian signature?
But you should not. Lorentzian evolution has to do with point one. It's only justified when these conditions hold. But the reason that this thing becomes complex is that those conditions do not hold. So evolution in Lorentzian evolution in time is not a prediction of the wave function at that stage.
This sounds to me more like just a prescription for setting up a state. This is the sort of thing we can do in quantum field theory as well. And then we're only really describing that state starting from some particular time. But that doesn't give a complete account of what happened before that in real time.
Maybe I could try this again. So in this bigger framework, which I just alluded to, right, you have Lorentzian histories, and it's just sort of like field theory. And you have to construct the states, right? And one Euclidean methods are one way of constructing the state. You take that state, and from that you deduce probabilities for.
So in field theory, I understand how you could construct a state
and
that
prescription reduces to this.
Sure.
Right, in the semi-classical.
So that gives you a state at some time t and later, t naught and later. But in that quantum field theory, you could also equally well take that state and evolve it back.
It's not quantum field theory because we don't have a fixed background space-time.
I understand, but in the analogy.
In the analogy,
I agree.
Yes,
okay.
But here there is no quantum field theory background.
But are you saying that time begins in some sense at a finite?
By time you mean classical evolution?
Yeah.
Yes, I'm saying there's a fuzzy beginning. This emerges gradually.
So it
from
is kind of like
quantum mechanical evolution.
I was told not to use the term tunneling from nothing, but it sounds to me like that's what you're saying.
No, I think it is analogous. I think it is related. Sure.
Tunneling from nothing.
Why can't we?
From nothing. Stephen and I did that in the first paper, and I regretted it. Endless controversy.
Well, actually,
Okay, so I'm really sorry. I'll say one more thing and then stop. But we do have a classical analog of this in string theory with these winding tachyons that can sort of turn off and give a beginning to ordinary time evolution. So that picture is reasonable to me in that context where I feel I understand it a little bit better.
Yeah.
And that
But then-
is actually a kind of
No, no.
decoupling analog of what I thought this was. But
then you have
so I'm
kind
not
of
objecting
three-
to it, I'm just trying to understand if that's what's being said here. And it sounds to me like it is, but I'll shut up now.
Maybe I'll add one other small comment since tunneling from nothing came up. So, there's another picture of something you might call tunneling from nothing, which produces a different boundary condition, more like the Vilenkin kind of boundary condition. So, that I think illustrates some of the ambiguity in trying to figure out which are the right boundary conditions, so to speak. Near zero size for the geometry, roughly speaking.
Yeah, okay. Okay, so this is a very crude evaluation of that wave function in a mini superspace model with perturbations. And so the boundary data here are the values of the perturbations and the scale factor, the scalar field. And this is the zero mode essentially, and these are the perturbations. And evidently, if epsilon is and epsilon is a slow roll parameter. If epsilon is much bigger than v, or than h squared, then this really describes, it sits squarely in this regime where we know how to interpret the wave function in terms of an ensemble of perturbed histories characterized by those functions of time now, because for each background. And so we have an ensemble of perturbed classical cosmologies with a relative weighting factor given by the that's the exponential of the prefactor that I wrote down here. So the wave function, how you can even think about it? Well, when the scale factor increases, the wave function describes a kind of branching process, and in the end, you end up with an ensemble of slightly perturbed cosmologies, which differ in the details of the specific patterns of the fluctuation. And that it does so for each value, and revealed at the cell.
Isn't there something missing at this point, namely decoherence?
Ah.
Okay, right? Because these
Yes,
different
sure,
perturbed things were quantum superposition.
Yes.
Right?
So we and everyone else in cosmology assume decoherence. That's clear. We have to assume this even before we start talking about probabilities and for histories. That's clear, yeah.
But, I mean, decoherence is not something that just automatically follows from the WKB approximation.
Absolutely.
Being valid.
Absolutely.
Okay.
Absolutely, yeah.
But
I'll make a comment about that.
Take gene scheme and actually compute the full decoherence functional and see whether there's
Well, but Jim never did so in the case for gravity.
The problem is not so much calculating decoherence, it's understanding coarse graining of geometry.
Yeah.
What do you mean by dividing geometries up into different coarse grain classes?
Right.
Right? You can do that on a lattice, but that's sort of, it's a problem that I think is unsolved even in the classical theory. Exactly what is the measure that says that our universe is close to a Friedmann universe?
So strictly speaking...
So that's not under control. And so we admit it, assume the decoherence, and off we go.
On the other hand, so this is the traditional slow roll phase of inflation and the kind of inflationary universes. In this case, just written down in terms of the language of quantum cosmology. However, when you're in a very different regime, when epsilon is less or equal than v, so this is typically in the convention, in most of the inflationary models, this is way up the potential, beyond the last 60 d-folds. That's the regime which is referred to as eternal inflation. You see straight from the wave function that these guys, that the variance is large, in fact, that these guys can have a large effect on the classical evolution. And in fact, if you were to add this term, and if you were to evaluate the classicality conditions, which I require in order to do any normal cosmology, you would find that the gradients with respect to phi of the phase are not large compared to those of the M. That's a wave function way of saying that the perturbations in eternal inflation significantly disturb the classical slow roll of the field and lead to quantum mechanical behavior. So in this regime, psi, and that's my first remark, has support over a broad range of inhomogeneous geometries, and it describes an ensemble of quantum mechanical histories. And now Tom's question is more pertinent, of course. Here we are on more shaky ground, whether those histories actually decohere. I think so, but I mean, no one can evaluate this precisely. So in a way, what's happening in this regime is that the branching of the wave function is much more significant. Here you had a kind of a classical, approximately homogeneous ensemble of cosmologies. In this regime, it's the branching of the wave function which produces very different geometries, an ensemble of wildly different geometries, which cannot be interpreted in terms of a simple, what we call classical ensemble, an ensemble that obeys these two criteria.
And Thomas, wasn't that question already answered by this work of Barvinsky and Kamenschik that you mentioned? I mean, if they've calculated this, then they should have also answered that kind of question, no?
No, I don't think they were interested in classical behavior. The calculations that I know will concern loop corrections, but that's different from No, it resonates. It resonates, of course. What I'm saying here resonates with stochastic inflation, and certainly the approach to it that was developed by Stravinsky.
Yeah, sure.
Because stochastic inflation, what is stochastic inflation in the regime of eternal inflation? It's a large effect that yields wildly inhomogeneous geometries and prevents this clean classical evolution that you have in slow roll.
Just an effort to understand. When you say histories, related to Jim comment, you mean fine-grained histories or you mean coarse-grained histories? And if you, in the second case, what is a coarse?
Good, very good. Yeah. Okay, so we mean histories sufficiently coarse-grained for them to behave classically. Of course, if you're going to real fine-grained histories, there won't be classical behavior at all. So here, in eternal inflation...
Do you have control of that? How much are you...
Yes. Well, we have control of the classical behavior, yes, because we have these two criteria. But
coarse graining for the coherence to jump in?
We assume that once the wave function predicts classical cosmological behavior according to deterministic laws, that the coarse graining and the decoherency is okay.
Has happened.
Yes. So this is not the case here. So you could ask the question, how can we recover classical behavior? And the answer to that is, well, we have to coarse grain further, right? You could go from here to here simply by coarse graining. And what do you do, or what is the bottom line of that coarse graining? It is very much like imposing an IR cutoff.
Yeah.
An IR cutoff where you essentially don't keep track of all these branches, you don't follow all these modes in the regime of eternal inflation, but you sum over their probabilities and you sum over their... so you consider a coarse-grained class of histories. What are those histories? Well, those histories those coarse-grained histories are very similar to what we have in the slow roll phase. They're homogeneous on very large scales, and we retain patterns of smaller scale fluctuations which are relevant for observations.
So here you're trying to do something kind of hard. You're trying to describe slow roll eternal inflation. But wouldn't it be easier to describe false vacuum eternal inflation? Isn't it clearer that that decoheres and you just fits into your framework above? You just have these tunneling events.
Yeah, sure, sure. Sure. You could include false vacuum decay, and yeah. So let's label the different kind of inflationary patches by some index J, and those could be false vacuum or otherwise. But in the false vacuum, you would still have this kind of behavior. This would be, in your language, the proliferation of tunneling events, which also
that's right. But it seems clear that those tunneling events decohere.
Sure.
That's
sure.
That's the only comment.
Sure. Yes. Okay, so we could recover classicality, even in internal inflation, by coarse graining over these very large scales, and a very crude way of doing this is just imposing an IR cutoff. What you have then is very large universes with small scale fluctuations. It's very important to bear in mind that once you do that coarse graining, you've lost all information about those very large scales. That's the essence of coarse graining. It's gone. It's summed over. There's no information left on those, of the dynamics of the universe on those scales.
So, Thomas?
Yeah?
So there's a kind of intermediate point, okay, where, you know, the fluctuations are kind of getting large, okay, but they're not yet at the place where they're out of control. And
yeah.
I have always heard it described that, yeah, well, that would mean that there's some large fluctuation in delta rho over rho is pretty big, and that could lead to a collapse that we will eventually see. We haven't seen it yet. How does that story fit into what you're saying?
I was wondering about exactly that last night.
Okay. Right? I mean, this is a story
I
that
understand what
people-
you're saying. Yes, yeah.
No, I mean, Andre has said things like this.
Yeah.
Also, yes.
Yeah.
Long before you.
Yeah.
No, I agree with you.
Okay, so the logically it all fits together in the sense that if I put in this IR cutoff and I exclude those fluctuations which could lead to a future collapse, I cannot ask those kind of questions. That's kind of clear. If I'm asking a question
But
about...
that sort of suggests that there's some predictivity of those things. I mean, some consequence for the classical behavior that you thought you had, right? I mean, this picture, you've got a classical universe, and it goes and does all the nice things that it wants to do.
That's right.
People have suggested, at least, that sometimes we could find in our far future that the universe collapses on us because of that.
Yes.
Now, there are different kinds of large fluctuations. I guess you're talking about large scalar fluctuations.
Yes.
Yeah.
And you can also have, large tensor fluctuations, at least. There's been discussion of that. And
no understanding whatsoever of that.
yeah, but I would say it's less clear that leads to something which collapses then.
Absolutely.
It leads to long-scale inhomogeneity.
Sure.
Yeah, and
but you're absolutely right.
There may be different scales that are relevant depending on your inflationary scenario.
Right? What we have in eternal inflation is classicality, classical behavior in patches, just like what Carlo was saying yesterday for black holes. And if we say, okay, we want to recover full-scale classical behavior, we have to coarse grain, we do away with those fluctuations, but it prevents us from asking certain physical questions or questions which might be physically interesting. What is the fate of those classical patches? I think that's clear.
Thomas, so there is in QFT approach to this problem, you know that when epsilon is positive, that kind of acts as a regulator on the infrared. So wouldn't you be able to like separate this product into the parts that are
The problem is that
infrared and the parts that are above this scale,
so
and then somehow subsume the deep infrared part into what you call classical?
No, but the problem is that all those calculations, we heard a lot about that in the previous weeks, they assume perturbation theory. And you have to be able to go beyond that. This is a regime where the
But I mean,
perturbations are large.
In order to progress, you have to have a small parameter somewhere.
In order to progress in perturbation theory. Yes.
But also here.
No, but well, here on observable scales, it's fine. Perturbation theory holds.
So curvature scale is a small parameter.
I can do my
I mean, somehow I suspect that curvature scale must be a small parameter also in your approach.
I think that depends on the model of inflation. If you take chaotic inflation, there are branches of the wave function that zoom off all the way to the Planck density, where even curvature is not small. Maybe in this Volkswagen case, that's possible.
Do I understand correctly here that one of the messages, which is new to me, is that the coarse graining that works in this context is infrared, not the large distance?
Yeah, sure. Yeah.
That's a message, which is... Okay.
Yeah, so that's the curious thing about it. Yeah.
Okay.
Yeah. Okay, so with this coarse-grained set of histories, which are approximately classical and have small-scale fluctuations, they're good for one thing. And so that's that's the second item I want to discuss. They're good for calculating at least approximately probabilities for local observables like CLs. Now you might think this is hopeless in the no boundary state because of this factor driving you down to very small values of the potential initially, and therefore very few e-folds of inflation, and therefore essentially small and empty recollapsing classical patches. However, so that's the zero mode problem that Juan mentioned last week. Yeah? However, these probabilities given by the wave function are not directly related to our probabilities for our observations. So we claim this is not a problem. We claim that we test theories of quantum cosmologies by conditional probabilities, by relations between our observational situation, on the one hand, and one or another observable, like the CLs, that we're interested in.
CLs are the components of the mode expansion. What are the CLs?
So the CLs are
the expansion of the
probabilities for the CLs are derived from the wave function of the fluctuations, and they're the mode expansions of the CMB and SL. And our observational situation is some specific local pattern which specifies to some degree our observational situation, like launching the Planck satellite or whatever.
So in Juan's talk, the question came up of why prescribe the positive curvature for the spatial slices, say.
Yes, this is the same. This factor would seem to favor, so he calls this the zero mode, and would, because of the pressure of the 1 over the potential.
But so I understand, but if you chose zero or negative curvature, that went the other way.
Yeah.
So
perhaps. Yes.
Positive is a very, very special choice, but I'm not.
Yeah, it's kind of. Yeah. Okay, I think this comes back to the question: why this state, and can we derive this state from fundamental principles? In any case, I don't think this is much of a problem, this zero mode. You can debate whether it's a good theory, but these conditional probabilities are the way to test the theory. This is what we mean in quantum cosmology by we're going to do an observation. This is to establish a correlation between the Planck satellite and some data. And these conditional probabilities of course, both are ingredients inside the universe and determined by those guys, but they're very different from the unconditioned probabilities. So we evaluate them in the ensemble of histories, where we sum over all kind of inflationary patches of any landscape we might have. And so they evolve the probability of the observational situation. And so we have the values of the modes as well at the South Pole, the coefficients of the modes. So that characterizes our ensemble. And then we have the probabilities, in fact, of the actual ensemble of histories. Those guys is what you see up there. Those guys are the coarse-grained probabilities for histories. And the key point is this factor. If you're interested in conditional probabilities and requiring the specification of a certain observational situation, evidently, when the universe is very small, so for values of phi at the South Pole, which only give you a few ethyls, then it's very unlikely for a specific pattern, for a specific observational situation to exist. And so what's happening in this conditional probability is that the no-bound, the Hartle-Hawking prior, if I draw this in a given patch, say, the Hartle-Hawking prior favors a small number of ethyls. That's the bare wave function, say. But this conditional probability favors a lot of ethyls because in a big universe, a given observation situation is more likely to occur. And in fact, it flattens out, you might argue, once you reach the threshold of eternal inflation, which seems to produce exceedingly large universes, in which the probability for a given observation situation is essentially 1.
But you are saying that you're on the tail of your wave function, right?
We are saying that we are
so you had
in the middle. Yeah, the product will be.
No, I mean, but as you wrote,
in the middle.
Sorry, but as you drew the psi HH squared, you're on the tail. Whereas
Yes,
if you had
yes.
chosen some other wave function out of the hat,
Exactly.
you might have
Right.
not been on its tail. Would you?
Yeah. Would you prefer that?
Yeah.
Yes. Right. So what's clearly happening here is that this is very different from this in the Hartle-Hawking state. I claim this is the actual way in which we test the theory, and the Hartle-Hawking state does not disagree with observations, as I will explain. But you might certainly argue, well, it's a better theory in which it doesn't matter whether we put in our observation situation or not. Okay, the judgment is out, I think. Yeah,
So does this
I have no
imply
more to say about that.
Does this imply that we should have the absolute minimum amount of inflation that would allow us to be
So the
here?
question is where this peaks.
Right.
And it peaks at the threshold for eternal inflation. So if I have a model of inflation, just a quadratic model, say, somewhere along high of the potential, so we observe this part of the potential, the last 60 ethyls, but higher up the potential, we hit that regime of eternal inflation, where epsilon is less than v. That's where we hit the ensemble of universes which become exceedingly large, and that's where all of a sudden this rapidly rises to 1. You might argue, well, why don't we go even further up the potential? But then there's the boundary weight putting you down again. So that's the origin of this peak. This peak is a combination of the two factors.
But how do you know that this first factor, grows up to eternal inflation? I mean, I would have sympathized with what he says, minimum number of ethyls.
Because it's a specific pattern.
Do you know how to compute that?
You can just assume that a specific observational situation has a very small probability to exist in any Hubble volume, right? I specify you sitting there with enough data, and this is an easy calculation that this is going to be rare in a Hubble volume. So then the probability for this particular configuration is 1 minus 1 minus PE times the number of Hubble volumes. If the number of Hubble volumes becomes exceedingly large, which is plausible in the regime of eternal inflation, this is 1. But if you go below eternal inflation, you're into this approximately homogeneous classical regime where the number of Hubble volumes is finite, and you can easily drive this down to 0. So in fact, the second factor, if you specify your observational situation to sufficient precision, it's very short. That's the origin.
So there's some histories that eternally inflate, right? So you have a finite probability for those, right?
Yeah.
And those histories have an infinite number of Planck satellites in them, right?
Yeah.
So I think in those things, calculating the probability of the CLs is ambiguous, and that's the thing that the rest of us usually worry about in trying to understand eternal inflation, is when you have a history with an infinite number of Planck satellites, how do you predict which outcome we should see? But do you want to tell me that I shouldn't worry about that ambiguity because in any case the probability to eternally inflate is low?
No. I'm telling you, you should worry about it because this is the peak of the probability distribution. So this is the background in a given inflationary patch, which is selected by the Hartle-Hawking wave function.
Yeah.
And therefore, the probabilities for the CLs are going to be the ones associated with that coarse-grained saddle point background, which yields unambiguous predictions for CLs. But I do have a sum, and this is where the ambiguity comes in again. Well, it's not an ambiguity, but this is what you call an ambiguity. I have a sum over all eternal inflation patches in my landscape. They will all come with a certain weighting factor. And so, to conclude my second item, the recipe for prediction is 1. You look for the inflationary patches in your potential. Recipe in the Hartle-Hawking statement. Secondly, you identify the eternal inflation patches. Thirdly, you look for the lowest one, consistent with the rest of your conditions. And 4, in that one, you calculate the CLs associated with that one. And those are the predictions of the
I don't understand how to calculate the probability for the CL in a history that has an infinite number of iterations of us.
The point is that it's a coarse-grained history. So as I was discussing earlier, we go from here to probabilities for histories by further coarse graining over the large-scale structures. That coarse-grained ensemble of histories is classical and has only small fluctuations, which are statistically the same in all Hubble volumes. And that's what enters here.
So
now you might object, well,
histories, you don't have like infinite numbers of bubbles of different kinds?
They're all coarse-grained over. And where do the different kinds enter? The different kinds enter in this sum. So the difference between a quantum cosmological picture of eternal inflation, and now I'm drawing something I don't believe in, but okay. So let's draw all these different kinds of bubbles. In quantum cosmology, they enter as different. So say that these are different kinds, different, statistically different predictions for CMBs. In cosmology, quantum cosmology, they enter here as separate saddle points.
Because you coarse-grained.
Because you coarse-grain, first you put yourself here and you coarse-grain over the rest, then here, then there, and so forth.
But that's not what I didn't have to do that in my in your picture, right? I could have just taken your psi, and then I could have just done semi-classical evolution.
Oh, no. But once
I would
you
have included tunneling, and it would have had all of these different bubbles. Right?
sure, that's what we had. That's what we had here.
Yeah.
At this level.
Yeah.
But once I'm interested in predictions for local observations, I better coarse grain in order to have well-defined probabilities for coarse grain classical histories. Yes.
The problem with infinity here is in the eternally inflating case, in order to compute that probability in the sum, do I really have to compare different infinities? Because there are an infinite number of copies of every possible realization of the CL. And
infinities don't really end, right? This probability tends to 1 for large universes.
Right, that's the probability of...
That's the probability of this conditional factor. You might wonder, well, maybe this is infinite, or an infinite number of patches, but okay, let's not go there. That's another layer of infinity.
There are a couple of things that I'm confused about. First of all, the sum that you end up with is infinite. Is there some expectation that there's one particular history that dominates that
This is
sum?
not an infinite sum, and this is the sum over...
Sorry?
This is not an infinite sum. This is from 1 to 10 to the 500, right? All the different inflationary patches. And yeah, maybe I didn't explain this properly, but this is what you have in mind. What you could have in mind is some landscape potential with a finite number of inflationary patches.
In the landscape potential, things are not labeled just by where I end up. They're also labeled by how I got into the basin of attraction of where I end up.
Right, and there are infinite number of topologies. The 10 to the 500 is out of a hat. Really.
Yeah, okay. But no. We populate the landscape by these saddle points, not by how you end up. This is how we end up there. This provides the amplitude to end up somewhere.
So no going from one to another.
That's coarse grained over.
No going from one what to another what?
No.
From one vacuum to another.
Wait.
So you ignore completely Coleman-DeLucia transitions?
No, we coarse grain over it. A Coleman-DeLucia tunneling, once you are already in some classical universe, what is a Coleman-DeLucia tunneling? It corresponds to some branching.
Wait, so that your slice of on a time slice of your geometry, there aren't domain walls. You're not allowing that, or
Again, here, all the stuff is there. Tunneling, domain walls, whatever. When we go from here to there, well, I've wiped it out, but we do a coarse graining. Because the individual probability of any of the configurations that you have in mind is 0, okay? 0, because it corresponds to some infinite branching of it corresponds to one particular branch of the wave function, in which you have kept track of all tunneling events and so forth, producing some big structure. Okay?
Sorry, I'm sorry.
Now I'm interested in local probabilities.
Okay, so how do you know that weighting, that coarse graining, gives you such a simple weighting of the different probabilities?
Good. This is the key open question. I've done it approximately. I've assumed that not keeping track of subsequent branchings is not dividing the probability up all the time and just ignoring all those branches. All these branches divide up the probability, right? This is quantum mechanical decoherent branching.
Right.
If I'm not interested, I keep my probabilities as they were. That's the key assumption which I would like to, which is correct at zeroth order, but that's clearly the open question. Yeah. But conceptually, this is clean.
Sorry, so globally, any realization has a bunch of domain walls in it.
Any fine-grained history? Sure.
No, I mean.
So you want to ask the question: is there a domain wall in our past light cone? You know, like is there some bubble that we see in the CMB because of some collision?
Yeah.
Can I ask that, or do I need to uncoarse grain a little bit to
Very good. You need to uncoarse grain a little bit. That's a question of the same level as what Tom was asking earlier. If I'm interested in the ultimate fate of my classical patch, I better don't coarse grain over fluctuations on the scales that are relevant for that fate. Sure. This was an illustration in which I was only interested in predicting the CMB on observable scales, not in those larger scales questions.
People in the world, I don't know if there are any in this room, who claim that we can see observable signatures in the CMB of these Coleman de Lucia bubbles colliding with ours in certain configurations. And there are big computer programs being run to see
Absolutely.
those
I'm not denying those
are.
programs. But then you have to uncoarse grain a little bit, right? You have to, the coarse graining is adapted to the question that you're asking.
So you're saying you're doing some approximation where you haven't taken that into account.
Absolutely, absolutely.
You're missing some of the predictions for the CMD because of that.
Yes, if I'm interested in those kind of predictions, I better don't coarse grain over all branchings, but I keep a certain amount of, I keep the structure on scales a little bit beyond the scale of our bubble, right? Or whatever question you're interested in. Sure. I did the full coarse graining to get this amplitude. That's kind of the cleanest derivation of this amplitude.
Okay, so there are people in this audience, I believe, they can contradict me, who also say that the determination of those probabilities depends on all of this structure that you've coarse grained out, right? I mean, certainly. Friends of mine who are sitting. Am I wrong?
Turning to friends.
No, absolutely. I mean, so we would say the thing you should focus on are these.
Yes. Yes, I'm wrong, or yes, I'm wrong?
Yes, you're right.
We would say you should focus on these, these histories where you get an, the eternally inflating histories where you have an infinite number of bubbles, and this.
Well, but they're all there as distinct saddle points. And we have not thrown away them.
That's not the.
It is that, Steve.
Well, let's assume that the landscape looks like the following. Every local vacuum that we ever care about to have observation has is nearby surrounded by eternal inflation, slow roll eternal inflation regions. Yeah. So we only care about how to get there from those regions instead of any tunneling. If we talk about prediction in that kind of toy model, I think we can try to use this.
Perhaps.
If you want to involve other things, maybe not. But there is kind of an imaginable landscape situation that we can ask this question. And I believe if we ask that question, I would say it's very likely to run into contradiction already. Right? Because your prediction is that our universe comes from the lowest possible eternal inflation region. If you look into the past, let's say we see 50 e-foldings like 10 years ago or something, and see 10 to the minus 5 fluctuations, you have to predict that once you see further e-foldings, once you have better constraint on these global modes, their amplitude has to be very large because that's how you approach eternal inflation regime. Right, so I would say it's kind of, in my sense, they're almost ruled out in the sense that the more e-folding you see, the earlier universe you see, you should expect delta rho over rho to be growing very fast on long wavelengths.
Well, typically, that depends on how many e-folds there are in between.
Yeah, but your theory strongly has a probability distribution strongly favor anything that brings the eternal inflation region closer to current time.
No, that's not the case, in fact. That's not the case.
Pi over V is very...
Not closer. Steve, it is the same. We are dealing with the same...
The sum shouldn't run from 1 to 10 to the 500.
Oh, okay, sorry.
It should run to all the different realizations of bubbles.
It's infinity.
It's
really
right.
No. This is not a sum over different configurations or realizations.
Yeah.
This is a sum over statistically different coarse-grained saddle point histories producing one bubble per saddle point.
Sorry, I made a mistake, but I mean the coarse graining procedure is the subtlety. It's that, that's where all the mysteries seem to lie. I mean, how you coarse grain.
The problem that everybody else calls the measure problem of eternal inflation, I believe,
I know what
has to
everyone
do
calls the
with
measure problem. I know what everyone calls the measure problem.
It has to do with whether the number sitting there is e to the pi over v,
Sure.
or something much more complicated and ambiguous that we don't know how to calculate.
And bigger, right?
Well, who knows?
Yeah.
I mean, we don't know how to calculate.
I agree that this coarse graining issue is
Yeah,
key to understand better. I certainly agree.
Yeah, that's kind of where the.
I completely agree.
So can I ask a
But
dumb question
conceptually,
about
this
the
is
course?
what's happening.
Can I ask a dumb question about the coarse graining? What I have in mind is, you know, in a statistical system or something, you coarse grain over short distance stuff, and then you get some effective long distance thing.
Yeah.
Here, I thought the picture was we have a bunch of fluctuations. Maybe they're bubble nucleations, or maybe they're, you know, perturbative, pseudo-perturbative ones. But how do you say with bubbles? How do you sort of average out the bubbles to get a particular one of these 10 to the 500 or I would say infinite number? How does averaging over them give you a particular one? I'm confused about that.
The saddle points give you all bubbles. One realization of all bubbles.
Again, sorry. A given slice has a bunch of domain walls. Just classically, it has a bunch of domain walls. It's not a single bubble.
Semi-classically.
Yeah,
I can make it classical if you want. I can catalyze the bubble nucleations. It's not really a question of tunneling.
Well, it's just a Hartle-Hawking version of the Kolmogorov instanton that produces.
I'm just saying, how do you coarse grain
Well, you neglect.
over a bunch of bubbles and get some?
You neglect all bubbles except one.
Average single bubble.
You neglect all of them and you look for the saddle point that produces that one.
What does that? I'm sorry. What does that mean? Produces that one globally?
Yes.
But why would that dominate over global slices with a bunch of domain walls?
It's not meant to dominate. If I'm saying coarse graining, I'm summing over all configurations. I said this explicitly. You lose information. So this one saddle point describing this one bubble is the coarse-grained amplitude for all possible configurations of bubbles,
Sorry,
in which I only retain information about this one.
Okay, so when you X out the others, it's not that you're saying it's that one vacuum everywhere. You're saying it's that one vacuum somewhere, and you're kind of tracing out the rest. Is that?
That's right. Tracing out, sure. Coarse graining, tracing out.
Yes. Okay.
Sure.
Is that sum over other bubbles a finite sum or infinite sum? Or?
But these calculations suggest that as I was saying earlier, every branching, further bubble nucleations correspond to further branchings of the wave function. With each bubble nucleation, you decrease the probability, right? Because the wave function goes through some complex phase.
Yeah.
And
but
so
there are a lot of places to do it, right?
It doesn't matter, Steve. You branch. The wave function branches. The probabilities decrease. So if you keep doing this and producing a very complicated configuration, indefinitely the probability of that particular realization is 0.
Yeah, of any particular one, but the
Yeah,
probability of not branching, of not tunneling, is also 0 because you have so much space.
Absolutely. This is why I said that this is the probability for this is the amplitude for realizing a bubble of a particular kind, say kind A, tracing out over whatever else happens elsewhere. That's the key. That's the amplitude. Tracing out. And then I repeat the calculation for a different kind of bubble. Again, tracing out. I'm interested in the total amplitude to produce a bubble of a given kind.
Okay, so suppose it is infinite, which I think all evidence points to.
What is infinite?
The number.
Sure.
You mean the number
There are different
of types?
infinities that we're talking about, but yeah,
which
indeed,
infinity are you talking
I'm
about?
referring to the number of types.
The number of vacuums.
But then you would also agree that the probability for an infinite specifically configuration is 0, right? It's an infinite branching that you're following. It's a very fine-grained history in which you've kept track of all quantum branching of the wave function. Fine, you can do that. But I claim we're interested in a coarse-grained amplitude for the different kinds of bubbles, irrespective of the large-scale structure, tracing over what happens outside. Evidently, we're interested in doing this for all kinds of possible bubbles where we could end up. That's this sum over J.
Yeah, I think Eva is asking, what if that sum over J is an infinite sum? Right?
Yeah, yeah, and
Infinite.
yeah,
An
I'm
infinite
saying
number
that
of different...
based, yeah, I'm saying that based on there being trivially an infinite number of topologies of compactifications, if you want to talk about the landscape. It's a huge assumption to say it's finite, just gigantic.
Okay, but this is a different infinity from what everyone else is worried.
I agree with
That's
that.
different.
Yeah, certainly.
Good.
But I think it's there.
Sorry, suddenly after all this discussion, I don't think it's different anymore. So can you explain again your P of CL over EI? So assuming my lowest possible eternal inflation is some de Sitter vacuum, and that's the dominating thing in that sum, and we start from that branch, right? That is, you start somewhere, you eternally inflate in that lowest vacuum. So your PCL, given that EI is the branching ratio coming from there to whatever thing you want to talk about later. Right?
Yeah, then you,
but
if
you have
let
to
him do all this, then you get the, like, say, the Boltzmann brane probability, so that you get, like, de Sitter equilibrium.
Yeah, and actually it's not coming from the lowest possible de Sitter vacuum. There's all this branching ratio built in that.
Yeah.
So it's not different from quite a few measures.
Well, that depends on how you specify your observation situation.
Yeah, you can use a very
say that we
CMB was 10 to the minus something.
No, you have to, well, no, you have to say something about Boltzmann branes in that case.
So Thomas, suppose we had a situation where the potential was such that there was one of these solutions that you talk about that sat us in the minimum that we happened to be sitting in and predicted our observations. But we also found that, you know, there was another place on the potential that we could tunnel to, and the Coleman-DeLuca estimate of the tunneling time was 10 to the 7th years. Okay. What would you conclude about that? I mean, you would say on the basis of just focusing on your first bubble that, yeah, we have predicted that there's some reasonable probability for our observations, but if I actually look further out at these other tunnelings, I've said, oh no, it's very unlikely that we're going to last as long as the universe actually lasted. Because
but the other tunneling is also in this sum, isn't it?
Sorry?
The other tunneling, the other bubble is in this sum. So
yeah, but the process of us tunneling into that other bubble, you've thrown away. You've, of course, grained over it.
No, I calculate.
You only, as far as I understood it, you only talk about things that go from the Hartle-Hawking vacuum to our bubble or somebody else's bubble, but not transitions between my bubble and somebody else's bubble that, you know, are a catastrophe from the point of view of my universe.
Yeah, first, if there is another decay channel, then it should feature in this sum, and then it depends on what the relative weighting is. But the second part of the answer is, it's again a question of what's the kind of question you're asking. If you're interested in the fate of our classical patch, I should not be coarse graining. That's clear.
What I'm trying to say is that in order to calculate these probabilities, you have to actually worry about the fate of our classical patch. You have to worry about other Coleman-DeLuca instantons. And then once you start doing that, you run into the problems, I think, that everybody else has with this business of how do I define the measure on the how do I define these relative probabilities?
Again, I was coarse graining to focus on a particular question, small scale CMB observations. If I were to focus on a different question, I would not have done this coarse graining.
The small scale CMB observations could have been made by some civilization that existed, 10 to the 7th years ago, not 10 to the 9th years ago, they would have looked somewhat different. But there could have been, a Planck satellite. Maybe not, maybe evolution is such that it can happen.
We can discuss this model indeed.
I just don't think you can ignore the transitions where our vacuum is unstable, and if you can't ignore those, you can ignore transitions in which our vacuum is created not by your process, but by tunneling from some other vacuum.
But Tom, here he has the probability to start with, it's not?
He doesn't. I mean, it has to be calculated. And I don't see why it doesn't depend on
these Kolmogorov events are they're Hartle-Hawking realizations of those. This is just a homogeneous example. But if I have a false vacuum, there's the Hartle-Hawking instanton that does that tunneling as well, and it will be included in this sum.
Yeah, they're kind of there in the Euclidean. That's like a more interesting Euclidean configuration of the domain wall, roughly.
That's right.
And what we're saying, though, is that it may be important to correct your classical evolution, the classical part of your evolution, to allow for these tunneling events.
Certainly, if they occur on a time scale of the last 10 million years, of course, then you should not be coarse-graining over those. Sure. But it's not a conceptual obstacle.
Sounds like there should be more, there should be more dialogue on this, but how much more time do you need to finish what else you had prepared? We can continue this, or we could try to give a chance. How much more time do you need for the rest of what you had planned?
Well, that sort of depends on...
Well, if everyone were quiet. In the realization of the universe, which has zero probability, where everyone is quiet.
Well, less than 10 minutes, I guess. Okay. If everyone is quiet.
Okay.
Is that okay? Or?
Well, I'm not saying that everyone should be, but
why don't we agree to defer questions for 10 minutes? Okay, everyone
shuts up for 10 minutes.
Try. All right. I wanted to say only two more things.
Ben, you're such a coward.
So the first thing I wanted to say was that, I can be very brief on this. So I claim this is a crude way, a very crude way for sure, to predict probabilities for local observations without asking many global questions. And it assumes a lot about how that coarse graining is done, but this is the zeroth order approximation in the Hartle-Hawking system. So you can apply this to concrete landscapes, and we've been doing this for the case of warp D-brane inflation, where you have the tree moving in the throat of a deformed conical, and so forth. I will omit the details, but I'm sure many of you know them. The mini landscape in D-brane inflation has the following inflationary patches. Potential, there are six fields really, but roughly speaking, there's a radial direction, the radial direction of the throat. And this is the kind of inflationary model that you realize in warp D-brane inflation. And the landscape comes about because there are various fluxes which can be different in the bulk of the Calabi-Yau, which feed into the potential felt by the D3 brane moving in the throat of a conifold region. And what can vary is the height of the potential, the height of the overall potential, the width of the inflationary patch, and also the slope at that inflection point. So there are various features of this potential which can vary. And the neat thing about warp D-brane inflation is that it provides you with a concrete microphysical setting in which you can generate that landscape. So we applied our recipe to that landscape, order by order. And so it's very clear in what then happens. I should say, in this landscape, focusing now on the inflationary patches, you have a range of different observationally distinct inflationary universes, where typically the tensor to scalar ratio is very small, and the scalar tilt can vary. It can be red or blue, depending on whether the last 60 E-folds started there or there. If you have the last 60 E-folds here, it's a red spectrum. If you start here, you get a blue spectrum. So now we applied this recipe. So these predictions, what is this? This is really the statistics, what I'm drawing here, not actual probabilities or relative probabilities, just the statistics of inflation realizations in this landscape. Okay, so how do we go about making predictions in that landscape, assuming we're in the Hartle-Hawking state? First, we select the inflation realizations of that potential. Then we look for eternal inflation realizations. And what we find is that eternal inflation realizations, not surprisingly, are those for which, at the inflection point, the potential is exceptionally flat. So it's a small subset of these warp D-brane inflation models where the inflection point is, in fact, that's the lowest V prime, evidently, is where the potential is exceedingly flat. So we select those. Then we go to the next level, and we say, well, what are the different eternal inflation realizations in this landscape? Then we come to this thing. The overall height changes, and so we're interested in the no boundary prior would drive you towards eternal inflation realizations of such a potential where the inflection point sits at a relatively low value of the potential. So we were driven down, and we were zooming in on a particular subclass of those warp D-brane realizations. And then the key question is, well, what do you predict? And you find that you zoom in on this very specific region. It turns out that all the lowest eternal inflation realizations of such a potential have eternal inflation at the inflection point, are red, and have an exceedingly small tensor to scalar ratio. So that's an illustration on how this recipe, which is evidently crude, but I claim conceptually clean, provides you with a sharper prediction than what you have on the basis of just statistics. And it's kind of neat because at the end of the day, what's in this prediction, it's information about the state and it's information about the landscape. It's really the combination of both that drives you towards a specific prediction. Maybe I should stop there. I have some holography stuff to say, but.
Now further questions are welcome.
So I think I can summarize what you just said as you're claiming there's a prediction of unobservably small r in the string landscape,
Yes.
because not because there isn't both possibilities, which we know that there is, but you're saying you look for the lowest eternal inflation possibility, and therefore you're going to always.
In this, so that's the intuition.
So can I turn it around? If suppose R sharpens around its current central value, will that rule out the Hartle-Hawking wave function combined with the string landscape? It's a yes or no question. I'm curious.
You can consult your
You're
lawyer.
cornering me.
You can consult your lawyer. Don't.
Now is the time to be making interesting bets, so I'd be willing to take.
Well, okay, so that was this example suggests.
No, I mean, not just that example. We can get if you assume that this kind of inflation happens among others.
Yeah, qualitatively, I agree.
Do you
agree.
want to make the bet?
We can talk about that.
R is bigger than what?
0.01. I mean, that's the obvious threshold.
Yeah. Yeah, all right. Yeah, I'll make it better.
So have I misunderstood? But I think in your model you can also calculate this V of phi. I mean, namely, you can calculate the amplitude Kobe normalization. Can you? No?
Oh, but this is not the potential in observable scales.
Okay, but cannot you in this model also calculate Kobe normalization?
Yeah. Okay, that's a longer
So you
story.
need to get something like.
That's a longer story, but the statistics of these models have varying Kobe amplitudes.
Yeah.
But
there is only, this kind of approach should, I think, allow you to calculate
that's right.
within that model.
That's right. That's right.
So what is it?
And you're driven towards small Kobe amplitudes.
But you cannot.
But typically the Kobe amplitudes are much larger than what's observed in those models. So you're driven towards the small Kobe amplitude subset of those models. Sure. Yeah, you're right. You can
I might have thought there would be another kind of coarse graining, and it seems like there's many uses of this term. So it might be, I think it's probably different than your use of the word, but a kind of coarse graining where you forget certain kinds of phase information, where you could take something like, well, Hartle-Hawking proposal and derive, in quotes, the Starobinsky proposal. You forget about phases and you get some kind of stochastic equation.
Yeah, it rolls out.
I mean, but is there, you think there is not just a resonation?
Starobinsky did this in 86.
But is there a derivation of?
I think there is in some cases. I think
pretty good, yeah.
Okay, so.
But it's different from what you're saying in the sense that as I understand it, the Starobinsky comes about when you coarse grain over a short wavelength.
Exactly. It's a different, and then you get sort of, you think you can compute long distance, complicated patterns, but
absolutely. Yeah. The stochastic picture of inflation rolls out of the wave function if you do not do the coarse graining over large scales.
But you coarse grain over something.
You do course grain over sub-horizon scales.
Okay.
Yeah.
Okay.
But you're describing fine graining, as I understand it, where you're kind of
fine graining.
You're kind of getting rid of all the long scales.
Yeah.
And then that's not clear that it's going to do the same kind of a thing because the coarse graining relied on you're relying on the fact that all the correlations are dying on times that are long compared to the Hubble scale, and because you got rid of all the short stuff. But in the opposite moment, it's hard to see that it's going to work.
But I'm coarse graining, yeah, sure, yeah. I'm coarse graining the probabilities. We're doing both.
So there's old-fashioned coarse graining where you coarse grain over fine scales and get Starobinsky.
Sure.
And then there's your new approach where you coarse grain fine grain. You leave out long distance scales. That's
Yeah. That was my confusion.
Oh, sorry.
Earlier.
Yeah.
Yes, in a way, fine graining would be, but it's a coarse graining over histories.
No, but it's you're focusing on this local thing and tracing.
There's something similar to that, by the way.
Yeah, but that's a coarse-grained history.
This business of trying to understand how to deal with, soft gravitons in the deep infrared. It's kind of analogous to a sum over soft photons when you are looking at, say QED.
Yes.
And you have these long wavelength modes. You don't care about them, basically.
Sure.
So,
yes.
At least I think it is. Maybe you could.
No, I agree. Yeah, but it's like your IR cutoff.
Well, yeah. I mean, that's kind of how we were thinking of it. Yeah.
Yeah.
Right. So it's just,
well, we too.
Weird to integrate out long.
It's an overloading of the term, so that's good.
That's right, yeah.
Tracing is maybe better.
Yeah, it's sort of writing an inclusive.
Right. Exactly.
Sum.
Yeah.
I mean, somehow you're doing that without generating the usual problems with integrating out long distance things.
Well,
which you normally don't do in field theory for.
No, in field theory you do that. Well, in QED you do sum inclusively, and that's how you get finite things.
Right, but you don't do a Wilsonian,
Yeah, it's a slightly different procedure.
Yeah, it's not the thing that would generate non-local.
Non-local effects. That's right. Yeah, it's a different kind of.
But there it's important to show that your result is independent of the infrared cutoff. You know,
Well, in some cases, well,
I mean, that, you know, you have to define what you're doing carefully to make sure you're.
that depends on the experiment, though, because
Exactly.
if you're sensitive to photons at, longer wavelengths or something, then it's not. Then the other matters.
That's
Because
right.
you've thrown
So,
them out, but
you
you're
have to,
sensitive.
that's a baby version of the measure problem.
I guess. Other questions? Okay, great. Thanks again.